Okay, so this is our last discussion, right? We will have exam next week. So I think it's a good idea to show you some more problems. Those problems are from previous exam, um, like a the same professor. So I think it's good to show you these problems and give you an idea like how will the exam problems looks like, right? Okay, so as usual, feel free to interrupt and unmute yourself, ask questions, right? And there are four problems in total. The first one, as you can see, it's about um, ideal Fermi gas at zero temperature in 2D. And the second problem we did it before. It's like a two system. One is outside the solid. Another one is on the surface of the solid. There's an equilibrium, and you need to calculate some quantities. This one is about, you need to it's also for Fermi gas, and you need to calculate the current, stuff like that, as we will do it in detail later. And the last one is about boson gas and the BEC, stuff like that. Okay, let's start with the first one. Maybe I'll give you like 3-4 minutes to read the problem and think about it. Then we can go through it together.
So when we see relativistic, should we assume like this linear dispersion and not assume that we're supposed to use the full like square root of p squared c squared plus m? Okay.
Yes.
Okay.
Yeah.
Cool.
Oh, by the way, for this problem, the n and the v should be given. N is the total number of particles. V is the, in this case, is the area of the system. Otherwise, it can, you can always scale your system, right?
So, but if it's high density, wouldn't we want to know if these are fermions or bosons?
Here, high density, I think just means it's zero temperature, and you need to consider the Fermi statistics instead of ideal.
Oh, it says it's electron gas. Okay, I didn't notice that. Yeah. Okay, thank you.
Okay, maybe let's do it together. Okay, I will solve all the problems in detail. So step by step, feel free to stop me whenever you want and get confused. Okay, so this is the 2D problem, and it's actually very similar to what the professor taught in class about the 3D Fermi gas, and the starting point is also similar. So I would say it's a good idea to kind of reproduce all the derivations that the professor did in the class. Starting point is, the energy is a sum over all the states, something like that. The number of particles is given by this, and also there's one more. PV divided by T is given by this. K minus mu, right? And this is a Fermi distribution. Okay, mu plus 1. This problem is even simpler compared with what you did in the class because it's zero temperature. Zero temperature means distribution becomes a step function, right? And this is your chemical potential. It's actually your Fermi energy, right? This is 1. This is Einstein's energy. So I just need to figure out like these 3 integrals. That's it. So let's do it one by one. Let's first look at this particle number, which is given. I'm pretty sure you know how to convert this sum to integral. G is the degeneracy. Let's put it here, and the dx dp square, and that. So this integral would give us the volume, or in this case is the area of the system. And dp squared. Remember, because it's in zero temperature, so this guy is a step function. So this integral is PF, right? It's integration over a disk. And we know how to do this integral. This is just a 2 pi p dp from 0 to PF, right? Which is given by 2 pi p square divided by 2 PF, which is pi GV divided by h square and PF square, right? This PF is what we need in later calculation, right? Because whenever we do an integral, there was always a cutoff set by this PF. Is it clear for this calculation here?
So are we assuming we know what the Fermi energy is?
No.
No, okay.
I mean, that's why we know N and V, right? So from this equation, we can solve PF in terms of the variables we know. Any other questions? Okay, so let me add another page. Okay, let's look at total energy. This energy is what we need to calculate, right? Energy is given by similar expression. And G is a degeneracy, dx squared, dp squared, and epsilon k, and something like that. V comes from the integration over the space, p squared. Similarly, we have this, and this dispersion is linear, so it's say p, and that's it, right? This integral give us, sorry, this factor give us this cutoff. And GV divided by h squared, just the prefactor. And this guy is given by 0 to PF. I'm converting this from the Cartesian coordinate to the polar coordinate, and 2 pi p dp, and we have this guy, so times cp. Right. I'm going step by step. So let me know whenever you get confused. P squared dp, which is 2 pi c gv h squared integration. This is easy to do, which is just a 3 pf cube. Right, and we know pf from the previous calculation, from this one. We just need to plug in and write this guy in terms of the parameters we know. That's the energy, right? Is it clear?
I have a question just to clarify. V is 2D, right?
Yeah, it's the area. It's the area.
Okay.
Yeah.
Thank
Yeah. Okay, so that is the energy. Now we need to calculate the pressure. So use this one. I don't want to rewrite it. I just copy it. Okay. So similarly, we convert this sum to integral. Oops. And integration of some log of 1 plus exponential minus beta epsilon p minus mu. Sounds like that, right? And so similarly, we have this and the log of this and the dp squared. Now we want to convert this integral from the Cartesian coordinate to the polar coordinate. So it becomes 0 to infinity. Remember here, there's no distribution function. So it's from 0 to infinity. And now 1 plus this guy. And 2 pi p dp, right? Let me add another page. I mean, the professor did this in class for the 3D case. I'm just repeating it for the 2D case. And now we need to do the integration by part. I put this pi in front of the integral, and this 2p dp, I will write as dp squared. Right? So from the integration by parts, we know that log the whole thing p squared from infinity 0 minus 0 p squared times the derivative of this log dp, right? So this constant, this term is 0 at the infinity because as you can see, there is exponential factor which decays very fast, faster than this p square. It will kill this p square. It will give us 0, and this at p equals 0 is 0, right? It's just 0. This term just go away. We have this term. So there's a minus sign, integration from 0 to infinity, p squared. Now we need to take this derivative. To take the derivative, I mean, it's just a log function, right? We know this one. And now we also need to take a derivative for this argument, which is the chain rule, right? Which is something like that. So this, let me write one more step. P squared, there's a minus sign. The minus sign. This derivative gives us minus beta partial epsilon p partial p exponential minus beta epsilon p minus mu. And now, also this minus sign cancel with this minus sign here. And h squared. This is beta is a constant. I factor out. This guy is also a constant because your spectrum is linear. This is C. And this p squared is p squared. And this guy at times the factor of exponential beta on the numerator and the denominator give us 1. Something like that. Okay. Right? And is it clear what I'm doing here? Let me know if there's anything unclear.
Should it be epsilon sub p minus mu in the exponential?
Or absolutely correct. GV pi beta c divided by square. Now you recognize that this guy is nothing but this distribution function, right? So it will cut the integral from 0 to pf. This is GV pi beta c square. This is 3 pf cube. Yeah, that's the answer. And this, of course, this is related to the energy. You can see they are both PF's cube, which is, I think is P divided by E, and the energy is write down. The relation is different from the one in the 3D. The factor is different, but they're still proportional. Let me copy this. So as you can see, PV, by the way, at times T on both sides, PV equal to, this T will cancel with this 1/T, right? So this GV pi C H squared, something like that. So PV divided by E is given by, so this guy cancel out, many factors cancel out. So the whole thing cancel out. Left with 1/1/2. So it's PV equal to E divided by 2. It's different from the 3D, I think. I think 3D is 3 or what? I didn't remember. Yeah, that's the solution for the first problem. Anything unclear?
Does it matter that we sort of took the beta to infinity limits like after doing the integral with the beta to infinity limit like already kind of done in terms of the distribution function?
I don't think so. I mean,
I guess it doesn't, but
yeah. I mean, as long as your integral or conversion is convergent, I don't think there's a problem.
okay, thank you.
Basically, you're changing the order of this guy, sorry, this guy and this integral, right? As long as there's no divergent things. Okay. I mean, if there's some divergence problem, it's always tricky, right? Okay, so the second problem I did, I think, in the week 8. So you can take a note if you want. Escape this one. So let's look at this problem. It's also a very fun problem. Maybe we're still like 5 minutes to read the problem and we can do it together. By the way, this W is nothing but a work function. Yeah. Okay, so let's do this problem together. Right, there's actually many problems similar to this one. Yeah, okay. So basically we have a metal and we have some, okay, let's draw in this way. And we heat it up with some temperature, I don't know, T gas. And so it will excite some electrons outwards and form some current. And in this problem, we basically need to evaluate what this current is, right? We know the work function and we know the chemical potential within this metal. So the problem A states the condition on the momentum for electron to be able to escape from the metal to the outside. Right, so let's assume the surface is right at this d equals 0. I mean, you can always do some reasonable assumptions. Then the energy basically is V square must larger than the work function, right? That will give us, this is a metal, imagine. Of course, your VZ should be positive. Give us a cutoff, critical temperature, so critical velocity in the Z direction for the electron, which is 2W divided by R square root. So your V must, I know the Z direction must larger than this value. Yeah. So for part B, you need to calculate the current density. So the current density is given by electron charge, the charge density, electron density, and also the velocity, the average velocity perpendicular to the surface. Right? So we only need to calculate this average velocity. To calculate the average velocity, we need to first figure out the distribution for this velocity for the Fermi gas. Right? So what is this guy? Let us write down the total number of particles similar to what we did before, sum over K and A, which is G. In this case, the degeneracy is 2, and V is a volume, and P, something like that. And this guy is nothing but beta V squared minus mu plus 1. Right? And divided by n on both sides, we got 2n. N is the density. Sorry, I think n is here. Yeah. Right, n, this small n is the capital N divided by the volume. Integration, this guy this P equal to M V, right? So it's M cube dVx dVy dVz. Awesome. That tells us the probability for this guy is nothing but the integrand. Oops. Sorry. Okay, so is this? Yeah, that's the velocity distribution for the Fermi gas. Yeah, any question about this part? Let me add one more page. So once we have this distribution, we are ready to evaluate this average velocity, which is given by, Vz T d x. So I think this way. Yeah, right. Is given by, I just plug in 2 and h cube integration over, for the Vy is from minus infinity to plus infinity. The same thing for the Vx. It's Vx and Vy. And for the Vz, we should integrate from the Vc, the critical velocity, to infinity, right? So then, and the current is given by En Vz. So we just need to change the prefactors. Copy. At times E, let's add a E here. And this density cancel out with this N in the denominator. So this is the current, the expression for the current. So the part B only need to derive the general integration representation for the current. Is it clear? Yeah, there are many similar problems. For example, we can ask, we can add some, electric field outside and ask you what is the current at some position, Z equal to Z naught. Then you only need to shift this critical velocity and get a similar result, right? Okay, so the part C, we need to approximate our results for sufficiently low temperature. So at low temperature, we can, so this factor, let's look at what is the smallest value for this factor. I mean, it's nothing but W minus mu, right? Because the smallest value for this kinetic energy is the only component is along the Z direction, and the minimal energy we need to for the electron to escape from the metal to outside is W. So it's minimum energy is W. And this guy is this guy is positive. That means when temperature goes to 0 or beta goes to infinity, this guy is much, much larger than 1. So we can drop this +1 factor here. Then this integral becomes a Gaussian integral, even though there's some cutoff for yeah, something like this. This integral is we can do it, and due to the time limit, I will just write down the result. It's just a Gaussian integral, right? Which is no. So eventually you would get 4 pi EM Q2 sounds like this. Yeah. So the current, the temperature dependence for the current is like this: T squared exponential minus some energy divided by KBT.
So the chemical potential did not appear in the inequality for the momentum in part A. Is that right?
Yeah. That's because okay, so like the picture we usually draw. This is W, and yeah, this is W and this is mu, I think. Yeah. If you say, okay, the W is the whole thing, then you just need to shift W to W plus mu, right? Then the mu cancel out. I mean, it depends on the problem, whether this W is the whole thing or just the energy from the Fermi surface to the outside. The whole idea is the same. Any other questions? Okay, sounds great. Let's look at the next problem. Okay, it looks very long, but all these parts are just hints. So you can take a look. I don't think we have time to go through it, but I will sketch the idea, like how to solve it.
It says under our circumstances, you can integrate the relation. What does it mean by our circumstances?
Sorry, can you say it again?
Where it says under our circumstances, you can integrate the relation dE over d mu. Just a little bit higher.
Under, wait,
It's the third line of the hint.
oh, okay, in the hint, okay.
Yeah.
Under our,
I'm just wondering what it means by our circumstances.
oh, okay, I guess means in our problem, right? And let's see. Right here, the idea is basically you regard E as the energy as a function of the chemical potential, and then expand the chemical this function around this phase transition point. So basically, your E, then your E would be proportional to mu, right? And then we know mu is a function of T. Then we get this temperature dependence of this energy E. That's what the hint is saying. It's kind of confusing. I agree.
Okay, thanks.
Yeah. Okay, maybe it's a good idea to just sketch how we solve this problem. I will post the note on CCLE, so you can take a note if you're interested in this problem. So as you can see this kind of distribution of this, there are several Fermi gas problems and also boson gas. Whenever there are boson gas problem, I guess it will always related to BEC, right? So yeah, the only interesting phenomenon we can have for ideal boson gas is the BEC transition. Yes. Nothing else. Right, so for the first one, first part, below the BEC, basically below the transition point, we need to calculate the CV. I mean, we only need to calculate the energy, right? The energy is given by K and something like that. Yeah, that's the integral you need to do for the first part. And mu equal to 0 because it's some T naught. We are in this regime. The mu is 0. We can do it. I mean, you did it in the class, I think. And also, the problem tells you the T naught. So that means, I mean, if you do this integral, there will be some unknown parameters in your final result. So you want to replace this unknown parameters using known parameters with the T naught. So to find the relation between the unknown parameters, for example, the mass with this known parameter T naught, you need to also calculate the number of particles right at this transition point. Then you find this relation, you plug in you get the result. That's basically how we solve the part A. Yeah, so for part B, just like what I said from the hint, I mean, it's not that obvious from the hint, but anyway, we regard this guy as a function of chemical potential. That is so what? Mu equal. We expand this energy around this transition point T naught. So it's something like this. We recognize according to this hint, it's just 3n divided by 2. That also give us the dependence on temperature. This mu equal 0 corresponding to T equal to T naught. So we only need to figure out this chemical potential, the temperature dependence for the chemical potential near this transition point. To do that, I mean, this is for the region above this temperature, critical temperature. To do this, we only need to make use of this n equal to sum over k and k. This is a function of chemical potential for T larger than T naught. From this guy, we can solve this. Yeah. Some T minus T naught, some power. You can do some approximations according to this guy, and once we have this chemical potential as a function of temperature, we can plug in. Once we have this energy, we can take a derivative, get the CV, and that's basically okay. CV temperature, you would get something like this as T naught. And that's basically how we solve this the last problem. There are many detailed details like calculation stuff, like how we get this mu T from this equation is very tricky, and other stuff. I wrote down all the details in my notes, so I think that's good. Okay, I think you're free to go if you have no questions.
Are there any other core examples or topics you think are good to know?
I mean, if you think about what we learned in this quarter, there are not much, right? Basically, several ensembles, like this kind of, and also the boson gas, Fermi gas, and what else? They're all free system. There's no interaction. And in principle, it's easy, but sometimes it can be tricky. Yeah.
I guess, do you think, I imagine on the final that most of the thermo questions will not be probably revisited?
Okay, so I don't think there will be a thermal problem, but I haven't seen the exam problem yet, and so
Was this a practice or was this a previous exam?
this is
or
a
both, I guess?
previous exam.
Okay, so based on this, it seems like probably not.
Probably not. Yeah. I would. Yeah, but who knows? I don't know. Yeah. Any other questions? It's next Monday, right? Not much time for you guys. I guess it's your first, the first exam, right, in the final week, Monday morning.
They were originally both scheduled for Monday.
Oh, wait, what's the another class?
E&M.
Oh, okay.
That would have been really fun, I think. We probably should have just kept it.
This is E&M B or A, B, right?
Yeah, the second one.
So, yeah, I think it's 11:30. Yeah, you can double check on the CCLE or not CCLE, or it's my UCLA website. I also didn't remember. Yeah, but in any case, so definitely there were problems like Fermi gas and boson gas, I'm pretty sure. Yeah. That's what you learn like after the midterm, right? Like that. The also the most, I think it's the most interesting part. Make sure you know how to kind of I think you solve the like the derivation the professor did in class as for both ideal boson gas and ideal Fermi gas. Actually, like in this exam, the problem A and the first problem and the last problem is basically basically what he did in class. Okay, so if you have no questions, let's end this discussion, and I guess see you next week, I think. Okay,
Thanks, G.
sure.
Thank you.
Okay. Bye
Thank
again.
you.